let me get the recording going here. So these two are pretty good problems in terms of just getting a sense of the concept. I recommend, and it's kind of, I gotta say, I'm a little inconsistent with this in practice, but I recommend doing, it's kind of like I should probably practice what I preach sort of thing, but put the function into your calculator first and get a look at what's going on before you even start the problem, just because it'll give you a sense of what's going on enough to know what you should be on the lookout for. All right. So when I look at a polynomial function, I look at the highest power. That highest power tells me the number of roots I should be on the lookout for. All right. So I see a power of 3, which tells me that I should be on the lookout for 3 roots. And in fact, that tells me that I should have 3 roots in my solution. Now they gave me one of them. Remember, I mentioned this a bunch of times. When they say a 0, they're saying the same thing as a root. Same as a root. All right. In 2-dimensional math, that's something that you can assume to be a fact. All right. When you broaden it out to other dimensions, then it changes up a little bit. But for our purposes, we can assume it to be a fact. Right. When they say 0, we see a root. 0, root, 0. So I'm looking for 3 of them. X to the third minus 16 x squared plus 80 plus 86. So plus 86 for crying out loud. 86x minus 156. Now, you may not get a good look at the entire graph, all right? But I could get a good look at a T-bone. No, forget it. So I see that there's a root there at 6. The problem is it's a triple root, right? Well, or is it maybe a single root with 2 complex roots? The problem is we're kind of flying blind here in the sense that there are 2 other roots. I don't know what they are, right? Am I dealing with a triple root? Is this close enough to acting like a cubic at that intersection? I don't know. I kind of feel like it should be the root around this location if it was going to be one of those multiplicity 3s. It's close. It's too close to tell. So we dive into the synthetic division process. All right. So 1, negative 16, 86, negative 156. Now the root is 6, so that's saying R is equal to 6. So the number that goes on the outside with synthetic division is going to be the 6. So I drag down the 1, multiply by the 6 on the outside, add, multiply by the 6 on the outside, add, that's going to be 26, multiply by the 6 on the outside. Oops, that should be in blue. Add, and you'll see a remainder of 0. All right. So that's a poor quality 6. Let me just kind of fix that. So I started off with power of 3 polynomial. Now I needed, I did synthetic division 1 time. So now I'm looking at a power of 2 polynomial. So I could tuck in an x squared, an x to the first, and an x to the 0th. And anywhere where there isn't signage, I'll just tuck in a plus sign. That's an assumed positive. But that's telling me that I need to go a little bit further. All right, so I have x squared minus 10x plus 26. I'm going to set that equal to 0, and then pick your favorite method for solving a quadratic. All right, bearing in mind that if it's irrational, so funky radical, or imaginary, negative under a radical, then it's not going to be as simple as just popping it into Desmos. Right? You'll have to use a technique like completing the square quadratic formula. We reviewed quadratic formula, so it makes sense to talk about that. So x is equal to negative b plus or minus the square root, poor quality square root of b squared minus 4ac all over 2a. All right, we have the understood coefficient of 1 in front of the x squared. That's the a value. We have the negative 10 in front of the x. That's the b value. And then we have that lone positive 26 off at the end. That's the c value. So x is going to be equal to negative, well, the b itself is negative, so negative 10 plus or minus the square root never make my radical long. Anyway, huh? Whoa, that's interesting. That's new, even for me. All right, plus or minus the square root of the b squared minus 4 times the a times the c all over 2 times the a. All right. Now, at this point, you know I'm a fan of Desmos, almost to the point of kind of being annoying about it. So I'm not going to subject you to like sliders or anything crazy like that. But what I will tell you is Desmos TI calculators, they understand order of operations better than we do. So the concerning part of this quadratic formula calculation is the part that's under the radical. That's the part that I would let Desmos take care of. Right? Because the most common error that I see is when people forget that negative 10 squared is positive 100. Right? They just say negative 10 squared and they put it in a calculator, they do it without the parentheses, and they come up with negative 100 for some reason. So just got to be careful about that. But if you type it into Desmos exactly the way you have it written on paper, assuming you have it written on paper correctly, it'll spit out the appropriate response, right? Or result.
How do you put it underneath the radical though?
Well, we're just going to actually physically write it under the radical and manually handle that.
Okay.
So we have the 10 plus or minus. I'm going to take that negative 4 and I'm going to put it under the radical. And that's all going to be over 2, because 2 times 1 is 2. So then when we go to simplify it, the thing about Desmos is it's very well tailored, and same thing with the TI to some extent. It's very well tailored to the real number system. There are workarounds that allow it to work with the imaginary or complex planes, but they're not user friendly without a lot more content knowledge. So at this point, what we would say is, all right, well, let's take a look at that square root of negative 4 and say, all right, how can we break that up? We could break it up. Whenever you have a negative under a radical, one radical always just gets the negative 1, a factor of negative 1. The other radical gets whatever the result is after you divide out the negative 1. The negative 4 divided by negative 1 is positive 4. Right. So it's the product of these two things that make a square root of negative 4. By definition, we know that the square root of negative 1 is equal to I. We know that the square root of 4 is equal to 2. Normally, I'd say plus or minus 2, but the quadratic formula already has the plus or minus built in. I'm not concerned about that. So I can now write this as 10 plus or minus I times 2. I'd rather write that as 2I over 2. And remember, you put a number next to a letter, whether it's I or an X, it's an assumed multiplication. I is representative of a particular number, square root of negative 1, but in many ways we treat it like a variable. Now we can go an additional step here, because there is a common factor on the top of this fraction. right? Both of these numbers are divisible by 2, so I can factor out a 2. All right, a little GCF action. So 5 plus or minus 1i, or just I, over 2. The 2's would then cancel, and we get our complex roots, 5 plus or minus I. All right, we were expecting 3 roots. We found 2 roots. They gave us 1, so we have a total of 3 roots. They say zeros, we say roots. So one takeaway from that, aside from the fact that it's not easy, but it's not as hard as that crazy one we did last time. So, I mean, comparatively speaking, I guess it's easier. But the one real takeaway from this is that there isn't much in terms of checking your work on Desmos that you can do. So you just got to check it manually and just look over everything carefully, right? But one thing I can say is, if you see a power of 3, but you only see 1 x-intercept, you have to be on the lookout for 2 complex roots. And before the course is over, you'll see some nice or interesting applications of this, real world style. So, it's just, we got to learn some more stuff involving trig before we can come back to this. The idea that trigonometry and imaginary numbers can kind of come together, that might be too ghastly of an idea to consider at this point, but it is something that we will explore down the road. Number 15, we have a power of 4 polynomial, and they tell us -1 is a double root. Double root means that if you take that -1 and call it r, you can use that in synthetic division for 2 successive attempts, meaning you can run the -1 through synthetic division just like we did with the 6 in number 14, and then take that answer and apply the -1 again, right? I'll show you that right now, but that's kind of a nifty thing to recognize if you notice that kind of relationship, right? I think I don't think I have an example of a more elaborate situation, but I think I'll make one up after this one. That's not true. I have several examples. They were just from a different lesson, but I'll steal one of those, and then I'll show you what I mean, all right, in more detail. It's kind of like a little nifty shortcut when it comes to, if you understand multiplicity, or if you took the time to really dive into that, then there's a payoff for you. All right, so we have coefficients of 1, -6, 5, 32, and 20. They're saying -1 is a double root, which means r is equal to -1. Just want to make sure I've accounted for every power between 4 and 0. The highest power is 4, lowest power is 0. Everything's accounted for, 4, 3, 2, 1, 0. So now I can start with my synthetic. Bring down the 1, multiply, I get a -1. Add, I get a -7. Multiply, I get a +7. Add, I get a 12. Multiply, I get a -12. Add, I get 20. Multiply, again by the outside number, I get a -20. Add, and I get a 0. I like to cordon off that little remainder there just to remind myself that it's not going to be a coefficient that I use in my polynomial. All right, if anything, it's a remainder. Now, I'm looking at this these coefficients that represent an expression. That expression would be a cubic, because it started off with a power of 4. After one turn through synthetic division, I'm down to power of 3. But because it's a double root, I can do synthetic division a second time. All right, so I can make another division bar, build off the previous work, and put that -1 on the outside a second time. All right, and again, that second time is because it's a double root. If it was a triple root, I would do it a third time. Right? It all depends on how many times the root is represented in terms of its multiplicity. Right? So a double root is another way of saying multiplicity 2. All right. So pull down the 1. 1 times -1, -1. Add. I get a -8. Multiply. I get a +8. Add. I get 20. Multiply. I get a -20. Add, and I get a 0. All right. So we went from power of 4 right on down to power of 2. All right. So we hopped down 2 levels. So we're down to x squared, x to the first, x to the 0th. Tuck in a plus sign here. The other term already has a minus sign, so we're good there. We can now write this as x squared minus 8x plus 20 equals 0. Now, I mentioned this right before we started number 14, and I said that I was pretty inconsistent with whether I do it and I should practice what I preach. So here we are with number 15, and I didn't do it. And that is put the function in before you even get started and see what's going on. All right. So I'm going to do it now, belatedly. All right. So I typed in everything that needed to be typed in. It looks like I got all the coefficients in the right place. I hit enter, nothing shows up because my window is a little out of whack. So I hit the home button. I'm looking at this graph and I see one root here at -1. It looks like a parabola around that root. So that justifies the double root multiplicity 2. I don't see any other points though. So I start zooming out. And the more I zoom out, the skinnier it gets. It never comes back down again. Right? If anything, I see a little bit of wobble right here, but it never actually turns back down to the x-axis. So if I do something like, in terms of my x-axis scale, going from like -2 to +2, this is probably the best I'm going to get in terms of a good look at the graph. I don't think there's another real root. All right, we got our 2 real roots. The other 2 have to be complex. So that's telling me to dive right in and go after it using the quadratic formula again. All right, so x is equal to -b. So -8 plus or minus the square root of b squared. So -8 squared minus 4 times 1 times 20 all over 2a. So all over 2 times 1. All right, so just popping right into the quadratic formula and then simplify. All right. Again, the only part that should be even remotely concerning when it comes to this should be the part that's under the radical. So we'll handle that separately. So I got a -8, close it up, square, minus 4 times 1 times 20. And now we have a -16. I'm not in love with the way my radical looks, so let me change that. It's still not much better, but I could put in my -16 there, and now I just have to clean it up. It's just computation. Right? What a lot of people will do when they see a negative under a radical is they say, all right, I'm going to pretend the negative isn't there. What's the square root? All right, if the negative wasn't there, the square root would be a 4. But the negative is there, so the negative means just slap on an I. All right, that's a good technique if it's a perfect square. If it's something that needs to be simplified, it kind of falls flat. But if that makes sense, then by all means, you don't have to show any of this work. But I'm going to show the work. So square root of -1 times the square root of 16. Square root of -1 is the same as saying I. Square root of 16 is the same as saying 4. All right, so I'm looking at 8 plus or minus I times 4, so 4I over 2. On the top of the fraction, I have a GCF. You can pull out a 4. 2 plus or minus I. On the bottom, I have a 2. 2 goes into 4 twice. So I could say as a final answer here, because we needed 4 roots. They gave us 2. We just came up with the other 2. 2 times 2 plus or minus I. Or if you want, you just multiply by 2. You can multiply through with the 2, which means that you probably only needed to factor out a 2 to begin with instead of factoring out a 4. But this is perfectly fine. In fact, better. It's the simplest factored form. All right, but I'm gonna create another example in a sec from a problem that we've already done. Just we're gonna kind of look at it in a different way. I'm just gonna pull it up on a different computer so I don't have to go scrolling all over the place looking for it. I mean, I will have to go scrolling all over the place. It's just a question of whether I have to do it with the camera rolling, as they say. Class notebooks, unit 2. All right, that one might be a little much. All right, yeah. I mean, it's a little much, but we're going to do it anyway. Good looking problem. Blank page. I'm just going to jot it down. So example, find the roots of p of x is equal to -5x to the 6th plus 35x to the 5th minus 95x to the 4th plus 125x cubed minus 80x squared plus 20x. And I'll take it as a typo. Throw this in the notes, like for good. All right, so I'm not giving you any of the roots, but we will use the calculator. And honestly, the calculator will tell you what all the real roots are. It's just a question of what you do with that information, right? So if you have to find the roots using synthetic division, then you have to go through the process and show all the steps, right? So what I would first do is take this glorious looking function and pop it in. -5x to the 6th plus 35x to the 5th minus 95x to the fourth plus 125x to the third minus 80x squared plus 20x. All right. So it's a crazy looking graph. Actually, from this vantage, it doesn't look very crazy at all. But when we start zooming in, it's going to look really funny. All right. So, but I don't really need to zoom in widthwise. You know, I could do it a little bit like this. It's really the height that I need to come in on. And so if I just kind of look at some of the y values here, you see really, if I'm just kind of going in the neighborhood of like -5 to 5 on the y-axis, that'll give me all the important points around the x-axis that I care about. So I hit my little wrench here and tap in -5, +5. Now I got a much nicer look at this graph. Right? You could even afford to come in a little bit closer because it peaks out a little bit less than 2. So if I want, I can actually bring the bottom end up to like -1 and the top end up to 2. Now we get a really nice look at the graph. All right. So if we look at this carefully, this kind of, it brings us right back to the beginning of the unit, which admittedly isn't that long ago, but it feels like a lot of content has been covered since the beginning. So it's worth revisiting. I'm going to save this one. All right, so here's our graph. I'm looking at this point right here. That has an R value of 1. It's a root that's equal to 1, but it also is behaving like a cubic. Right? It's behaving like a cubic around the x-axis. So that's a root equal to 1 with a multiplicity of 3. So you look at that information, say, okay, I guess that goes under fun fact of the day category. Now, it's actually really useful when it comes to synthetic division. That means that the number 1 is going to work in synthetic division 3 times. All right. So when I list out my coefficients, the -5, the 35, the -95, the 125, the -80, I'm down to power of 2, power of 1. There is no power of 0 term, so it must have been a coefficient of 0. I'm going to start my synthetic division with the number 1 on the outside. But once I get the result of this computation, I'm going to do it again with the number 1. And then once I get that result, I'm going to do it again with the number 1. And then see where that gets me. All right, the numbers may get large, but we have a calculator. And also, even if we didn't, they'll never get so absurd that you wouldn't be able to handle it with simple rote computation. And so I have -5 times 1, which is -5. Add, you get a 30. Multiply by the 1, still a 30. Add, we're at a -65. Multiply, we're still at -65. Add, we're at a 60. Multiply by 1, still 60. Add, -20. Multiply by the 1. Right? Multiply by the 1, you're at a -20 still. Add, you're at a 0. This is an interesting case because we haven't dealt with one where we have a 0 at the end. Multiply the 0 by the 1, you get a 0. And 0 plus 0 is 0 anyway. So we still have our remainder of 0. And now we have one less term, which is really the objective. We want to have one less term when we work with synthetic division. Because now we went from a power of 6 polynomial down to a power of 5 polynomial. because this is a triple root, I can do my synthetic division with the number 1 a second time. All right, so I'd bring down that -5 again, multiply, add, multiply, add, multiply, add, multiply, add, multiply, and add. One less term. We started off with power of 6. We did synthetic division twice. After the first time, it was power of 5. After the second time, now it's power of 4. We do it again, it'll be down to a power of 3. And we are going to do it again because it's a triple root. So I bring down the -5. I'm going to multiply. I'm going to add. I'm going to multiply. I'm going to add. I never remember the next step. Oh yeah, multiply. Add. Multiply. And finally add. Oh, that's not a little L bracket. There we are. All right, so then we're down to this, and it's like, oh, this is fun. And you look at it and say, all right, well, now what? Now we got a 4th degree polynomial. All right, I'm sorry, 3rd degree polynomial. Jeez. So this one was x to the 5th, x to the 4th. This is x to the 3rd, x to the 3rd, x to the 2nd, x to the 1st, x to the 0th. All right. Now we could go back to the graph and see if there's anything more going on, but we could also take a look and, we did all this work. We might as well see what's going on with this one. This is the same as saying -5x to the 3rd plus 20x to the 2nd minus 20. Since we have a coefficient of 0 here, that's just going to go away. 20x, sorry. So the 0x to the 0th is gone. I'm not worried about that. I have to put a little plus sign in there for fun, but this is irrelevant. This one, we don't care about it. 0 times anything is 0. All right, so I look at it and say I got cubic, but if I set this equal to 0, I also kind of reflect back upon my Algebra 1 days when we were learning how to solve quadratics. And I think to myself, oh, wait a minute. There were some situations where we had powers of 3, and even though there's a power of 3, it was still basically quadratic because all you had to do is pull out a GCF. Right? Remember that first thing that you look for when you factor is the GCF. Right? I'm looking at this and I'm saying, oh, wait, there's a common X in each term. I could factor that out. In fact, you could have factored that out right in the very, very first step. Right? But we didn't, so here we are. Right? It wouldn't have made anything any easier or more difficult, just a little bit different. All right, but if I pull out the x, I'll have -5x squared plus 20x minus 20. You could also pull, you could pull out a 5 if you want. You pull out a -5 if you want. But the thing that you have to pull out is the x. All right, so it's a question of, well, what do you want to pull out? Because we could set each of these factors equal to 0. And by the way, in doing so, we just algebraically discovered another root, x equals 0. So we knew x equals 1 with a multiplicity of 3 through the synthetic division process. We have x equals 0. Now it's just a matter of getting the other two roots, because we got 4 out of the 6 that we need, or that we needed. So maybe at this point you pull out a negative 5. X squared minus 4x plus 4. That actually happens to be factorable. So you don't even have to get into the quadratic formula. All right, so we could divide the negative 5 out of both sides, which will cancel it. So I'm not worried about that. Factor x minus 2, x minus 2. And so we'd have x equals 2 when we set each of these factors equal to 0.
Anyway, thank you, Isabel, for showing. That was very beautiful. Very nice.
I mean, I wholeheartedly agree. So we have x equals, so our answer, our roots, x equals 1 multiplicity of 3. We have x equals 0. If it only has a multiplicity of 1, meaning it only happens the one time, then you don't have to say it's multiplicity. You know, because it's not multiple. It's not a multiple. It doesn't happen multiple times. Right? X equals 2 has a multiplicity of 2. Right? So in all, we have a total of 6 roots, and therefore we have our solution. I mean, this is heavy duty, but the bulk of the work was done just using synthetic division. Yeah. And like I said, I just pulled this from our notes. We actually did this the other way, where we expanded it out from the roots to come up with the polynomial. The one I wrote down as the example, that was the answer to a question that we did earlier in the unit. Right. So I'm just showing you how you can go the other way with it. I thought it would be a cool exercise. Speaking of cool exercises, oblique asymptotes, the next topic, it builds off of this idea of synthetic division. But as surprising as this might seem, it is the easiest possible variation of synthetic division. All right. There is very little to do when determining the oblique asymptote using synthetic division. In fact, it's the kind of problem that you'll look at and say, wait, there's got to be more. I must be missing something. Right. So, but you'll see as we go through it, you won't be missing anything. It's just a nice, simple application of the concept of synthetic division. All right. So the problems here, they're kind of like a little review of rational functions. I lost the term there for a second. But we're going to skip these problems for now because they don't really add anything to the conversation. So we're just going to hop down to page 31. And the whole process is written out there for you, but I'm going to take you through one. It says determine the oblique asymptote for each rational function and graph. Right. In the last unit, we talked about vertical asymptotes and we talked about horizontal asymptotes. The only ones that we didn't talk about were the diagonal asymptotes, the slanted ones. Right. And if you remember, an asymptote is a line that a curve will approach. Right. And so we had horizontal lines that a curve approached, and we had vertical lines that a curve would approach, but we never had anything that was slanted. All right. So if the numerator's highest power is exactly one more than the denominator's highest power, that's this little notation here, then there is an oblique asymptote, assuming that there isn't a common factor. All right, because there could be a common factor that simplifies the expression down away from being a fraction. If that's the case, then it's something else, which we'll get to in a few minutes. All right. It's very simple. All we're going to do, if we have that relationship where the numerator has a power that is exactly one more than the denominator's power. Like in this case, the numerator's highest power is 2. The denominator's highest power is 1. That's a difference of 1. Right? In this case, the numerator's highest power is 3. The denominator's highest power is 2. Again, a difference of 1. 1 more on the top than on the bottom. Highest power of 2, highest power of 1. Again, a difference of 1 in terms of the powers. All right, all you have to do is divide using synthetic division. And if there's a remainder, drop it. All right. And there is an explanation for why you drop the remainder, but we have to learn about limits before you can understand that. So it's not a conversation we can have right now. Okay. So looking at my numerator here, we're kind of going right back to basics here with synthetic division. I can actually get my pen to work. This is the same as saying x squared minus x plus 0. Right? So coefficients 1, -1, 0. When you divide with synthetic division, whatever's on the bottom, if it's a linear factor, you set it equal to x minus r. All right, and so in this case, the x's cancel. And you have 1 is equal to -r, which means -1 is equal to +r. All right, so we're going to take that -1 and put it on the outside with synthetic division. Bring down the 1. Multiply by the -1. Add. -1 plus -1 is -2. Multiply by the number on the outside, you get a +2. Add. You get a remainder of 2. However, when looking for oblique asymptotes, we drop any remainder. So we just toss this out of there. All right, we started off with a power of 2. The result is power of 1. So my oblique asymptote which we abbreviate OA, is going to be in the form of y equals, we'll call it y, 1x minus 2, so just x minus 2. As far as the graph is concerned, that graph can be a Desmos graph. It's really just a matter of verifying. So let me just show you really quickly on Desmos. I'm going to put my original function in. Now, it is possible for a function to have multiple types of asymptotes. Like, for example, this one actually has a vertical asymptote also. And I can show you that real quick as well. So remember, and it's a good thing to review. Vertical asymptotes, and honestly, I don't even need these graph bars here. I'll take that as a typo also. Not really necessary. It would be more necessary in a non-Desmos world, non-graph and calculator world, but going to make necessary the word of the day. So necessary is the word of the day. The vertical asymptote, because it's been a while, again, abbreviation VA. I'm just going to remind you of the process. Set the denominator equal to 0. And solve. But again, it does rely on the denominator not being able to be simplified out of the expression by canceling. So if there's a common factor where that denominator would simplify out, it's not a vertical asymptote. But most of the time, almost all the time, you can tell visually whether or not what you think is a vertical asymptote actually is. So x plus 1, set it equal to 0, subtract 1, and you get x equals -1. Oblique asymptotes and horizontal asymptotes are conflicting, meaning if one exists, the other doesn't. So none of these examples will have horizontal asymptotes because they have oblique asymptotes. You can't have both an oblique and a horizontal asymptote. So if we're looking for an oblique, we only just look for the vertical asymptote and then we just move on. But let me just graph these for you real quick. So the vertical asymptote would be x equals -1. Make it dashed. I'll make it dot. I'll make it dashed. All right. So that looks like it could be a vertical asymptote, a line that the curve is approaching. So my oblique asymptote, y equals x minus 2, same idea. It should be a line that the graph approaches. Right? It does look like that's the case. As I move out along this path, it does look like that red curve is approaching or getting closer to the blue dashed line.